Hi, this is homework 1. Some of you have questions regarding this homework. So I'm going to do question 1 and 5 and 6 on this tutorial video. So for this structure, we're given that the cable over here has a diameter of 4 millimeters. Okay, and it's made of steel and it's a Young's modulus of 200 times 10 to the power 9 Pascal. Knowing that the maximum stress in the cable, so the stress allowable is equal to 190 times 10 to the power 6 Pascal, and that the elongation must not exceed 6 millimeters. So the deflection of BC must be less than 6 times 10 minus 3 meters. Find the maximum load P that can be applied. So there are two controlling factors over here. One is controlled by the stress allowable. The other one is being controlled by the deflection. Okay, so you do some standard stuff first. You write the data that are given, area of BC of the cable. So this you found as 12.5664, Young's modulus, and the allowable stress, the deflection. Okay, so we want to find FBC, right, based on deflection. So FBC is basically this cable over here, right? So this cable will be in under tension. Okay, so if you look at the cable will be in this tension. So this is your FBC. So you calculate FBC. Okay, so you use elastic deformation. So deflection, so this is based on elastic deformation. So from here, you found that FBC is equal to 2.091 times 10 to the power 3. Now, this is based on deflection. Okay, so you have to calculate the stress induced based on the 2.0912 times 10 to the power 3 Newton force, and you realize that it is 166.412 times 10 to the power minus 6. So much less than the allowable. So in fact, this is controlled by the deflection. Okay, so FBC is controlled by the deflection. If we were to use, let's do a side step. If we were to say the control is by the stress yield, so the stress yield we are given that is equal to 190 times 10 power 6. So you calculate that your force, so you know your yield is 190 times 10 to the power 6. So this will be your FBC divide by 12.5664 times 10 to the power minus 6. So you will get your FBC will be equal to 166 190 power 6 times by 12.5664 power minus 6. So you will get a 190 power 6 times by 12.5664 power minus 6. So your FBC will be equal to 2.387, right, times 10 388, okay, times 10 to the power 6 Pascal. Sorry, Newton. So if that's the case, if you have to calculate your deflection, okay, so you calculate your deflection of BC, so it's equal to 2.388 times 10 to the power 6. The length, okay, the length will be equal to 4 squared plus 6 squared square root. So 4 squared plus 6 squared, 7.211. Okay, divide, right? So this is the length, which is 4 squared plus 6 squared. So that is correct. So 4 squared plus 6 squared, and then the different PL over cross-sectional area is 12.5664 times 10 to the power minus 6, and then given their Young's modulus is 200 times 10 to the power 9. Okay, so the deflection is equal to 2.388 power 6 times 7.211 divided by 12, 664 power minus 6 divided by 200 power 9. So our deflection will be equal to 6 point, let me do it again, 2.388 power of 6 or power of 3, I think I've got this wrong, so 190 times 12.5664 power minus 6 is equal to 3, sorry, 6, yeah, right. Right, so this is cancel, this is power 3, 2.388 power 3 times 7.211 divided by 12.564 power minus 6 divided by 200 power 9. So the deflection will be 6.85852 times 10 to the power minus 3 meters, which exceed the stress BC allowable of 6 millimeters. Okay, or 6 times 10 to the power minus 3. So for this case, the control, if the control is the yield strength, the deflection will be this much. Okay, so that's why we pick the deflection controlled by the maximum elastic deformation. Okay, so that's where when we check, we say FBC is controlled by deflection. Then from here, okay, so we have found our FBC, right? So we have now to locate our BX. So we find our BX. So this is using similar triangles. Okay, you can use angles, the answer will be the same. Then your BX is this amount. And then you do static analysis about point A. Okay, then everything that is anti-clockwise positive. So the P when use anti-clockwise, the 1.16 times 10 power 3 will be clockwise, which so minus. So that's why your P, you calculate P, will be 1988.6 Newton. Okay, so this is for question number 1. Okay, so if we go into question number 2, okay, so question number 2 is a rigid bar is supported by the pin. Rod CB has a cross-sectional area of 500 times millimeter squared, and is made of steel A. So this is steel. Determine the vertical displacement of the bar at load B when the load is applied. So you will have your free body diagram. So you know that this is the triangle load, right? So this is over here. This is the equivalent load. So it's basically half base times height. Okay, from lecture notes we know why that's the case. And the distance from A, where the equivalent load is applied, is 1/3 multiplied by a complete length of 4. Then you carry out your your static analysis, taking your moment about point A, and you get By is equal to 30 times 10 to the power 3. Then you have to find FBC using similar triangles. So what do I mean by similar triangles? So if you look at geometry, right? If you look at geometry, okay, so this is 3. Yes, do apologize. So this is 3, and this is your 4, right? So this is 3, this is 4, and this will be equal to 3 squared plus by 4 squared, so it's equal to 5. Okay, so this is based on geometry. And then if you look at forces, you have calculated your By to be 30 times 10 to the power 3. Okay, then you over here you can get your Bx, right? And this is your F, I think it's your FBC. So this is your FBC. So that's what we want to calculate on our FBC. So you can form the, so FBC is taken with the distance 5 similar triangles, and this is equal to 30 times 10 to the power 3 taken over by the distance, the vertical distance 3. So that's how we form the equation. So you find your FBC and you find your deflection of BC is 2.5, right? So this is where a lot of people get confused. Okay, So there are a few assumptions that we make down here. Okay, I'm going to draw this triangle so you can visualize. We're going to assume, so if this is our transformation, so this is x, this is y, over here is rotation about z. So we're gonna assume that the deflection in the x distance is very much smaller than deflection of the y distance. Okay, that's what we're gonna assume at this stage. Okay, so the deflection x is very small compared to the deflection of y, right? So from here, I'm gonna draw. This is where my point C is. Okay, and then this over here, this will be my point B. Okay, so over here, this will be my point B. So what we want to determine, okay, what we want to determine is we want to determine this distance. You want to determine this distance. Where over here, right? Over here, this is our B prime. Vertically coming down. Okay, why vertically coming down? Because we say the deflection of x is very, very small. So over here, this is what we want to calculate. In the end of the day, we want to determine what is our dv prime. Okay, dv at point B, right? So this is one of our beam before loading, right? Then after loading, it became longer. So this is after loading. Okay, so I'm going to change this. Change this to a different color. Okay, so if we are going to draw our deflection, okay, so now this is exaggerated. Okay, I repeat, this is so this is our deflection. Okay, this is our deflection. So our deflection is this amount. Okay, so this is our deflection. And then we want to make, okay, what we want to do is we want to ensure, okay, geometrically, we want to ensure that this angle over here is 90 degrees. Okay, which it is now. Right? So now this is my 90 degrees. Okay, this is my 90 degrees. So what we want, so we know that the vertical one, so this distance from the red dot over here to here, this is your deflection or BC we have. This is what we want to find. Okay, this is what we want to find. So if I'm going to draw some other angles over here, a vertical one that's coming down here. Okay, so we have a angle down here, vertically coming down. So this angle over here, I'm going to call it my angle theta. Right? So if we draw, because this is vertically down also. Okay, this is vertically coming down, same thing. Oh, sorry, I should have drawn it. I should have eyeballed it better. Okay, so if this is vertically down, which it is, this angle over here, right, you can see it's also share the same. So this is also equal to theta. And remember I told you we deliberately want to make that 90 degrees. Okay, so from here we know that's why we can form this expression now. Okay, we can form this expression now. So from here we want to find what is our theta. Okay, so based on geometry, that you can see, so theta is this angle over here that we want to determine. So this is tangent, this is our theta. Okay, so theta is equal to 4/3. So sorry, tangent theta is equal to 4/3. So the angle you find is 53.13. Then you use cos. Okay, so why we want cos? Because we want to relate deflection BC with delta VB. Okay, so cos 53.13 is equal to deflection VC over deflection, the vertical deflection of point B, and then finally your answer is the same. The solution use a slightly different technique. Actually, it's not really different. The only difference that the textbook is trying to use is, I think, okay, I'm not wrong, they form this angle. Okay, they find this angle pi. Okay, and if they use that angle pi, if I'm not wrong, this is what the angle pi is also. Okay, so answers will be the same. Two techniques you see for yourself. Okay, so this is for question number 5. I think the most issue is this is where a lot of students are not sure. Okay, so it's not that bad. Question 6 is very similar to question number 5. Okay, similar in the sense that this diagram is still the same. Okay, I just use a different angle over here, similar to the textbook previous question basically, or the solution. So for this case, we have a rigid bar supporting a 800-pound load. Down here is where the 800 is. Determine the normal stress at in each cable. If each cable have a cross-sectional area of 0.04 inch squared. So we assume member ABD to be rigid. Okay, so to construct a free body diagram for this case, we know that both cables will be under tension, right? So that's why dy is going up, by is going up for this case. We are not asked to find AX. If we were to ask to find AX, we have, because over here, to complete the B body diagram, we have BX over here, and you have DX over here. So AX is not equal to 0. But we don't need that value. So we find our, we take the moment at point A, and then we form the expression. Okay, we form our expression, so equation number 1. And then we realize that our structure is statically indeterminate. Okay, then we use elastic deformation. Then we find the length of BC. We now what we have done is we find the deflection of BC. Okay, so we find the deflection of BC. We find the deflection of CD. And why we go into that? Because the structure is statically indeterminate. Okay. And then from there, again, exactly the same thing what I've drawn before is this relationship with dV. Okay, so again, we assume same thing. We assume that the deflection in x direction is very, very, very small compared to deflection in the y direction. Okay, or the movement. Okay, not necessarily deflection, the movement. Okay, the position. Right. So from here, you can find. So now I relate with the angle theta. So depending on what you're looking at, if you're looking at DC, you can find theta D. If you're looking at BC, you find theta B, like what I've drawn over there. So from here, you'll get your theta D and your theta B. Okay, and then very similar equation like what we had before, right? Very, 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 very similar. Then B prime and D prime share the same gradient. Okay, so what do I mean by that? So you have a structure like this now. Okay, so this is your point A, B, and D. So this is your point A, this is your point B, and this is your point D. So when they deflect on the same line, they share the same gradient. So over here is your B prime, and over here is your D prime. So over here, this is your deflection V at point B, I don't know why I call it C down here. It should be B. I do apologize. Okay, V, point B, or should be C. Nope, it's B. Do apologize. Right? So this is your point B over here to here. This is your vertical deflection of point D, right? So you have this expression over here, right? So at point D, so the distance over here is 5, the distance over here is 11. So they share the same gradient of 16. So this is your X and this is your Y. So I believe this is equal to this value over here. And then B, so this is delta V B. This over here is delta V at D. Okay. Then you find this relationship. Okay. And then you want to find what is BY in terms of FBC, right? What is DY in terms of FCD? Then you substitute into equation 1. So this is your equation 1 over here. Then we substitute everything. Then you discover, so after you substitute, we discover your FBC has this magnitude, your FCD has this magnitude, FBC. Then you find your stresses, and the answer is similar to what the solution state. So it's 11.4 and 15.4 KSI. So we've got 11.367 and 15.368. So this is homework number 1. Okay, some solutions that you or some of the proposed solution I made. Again, this is the big concern. Okay, where a lot of students, even myself, I just need to visualize. Thank you.